Thank you for downloading this presentation. I want to talk to you about a new technique for modelling the evolution of large natural fracture networks. So, in mechanically layered rocks, fracture networks often develop in the brittle layers in response to a tectonic strain or some other deformation. And because they're restricted to the brittle layers, they're often known as layer-bound fracture networks. Now, these fracture networks are important controls on the fluid flow through the layers and also on the mechanical properties of the rocks. And it's common practice to build digital geomodels of the fracture networks for use in fluid flow simulations or geomechanical analysis. Now, it's important to understand the scale of these networks. They can be very large because they can extend over geological structures that may be tens of kilometres in size, so they may contain millions of fractures, and they're therefore too large to simulate using conventional numerical techniques such as finite element models. Now, standard practice is to simulate these by building stochastic models in which fractures are placed in random positions and assigned random geometries to match the observations. But in a subsurface fractured layer, these observations may just be 2 or 3 boreholes across the entire structure. So we have very limited calibration data. There's a number of drawbacks to this method. Firstly, accuracy. Because we have limited calibration data, the models are often geologically unrealistic and poorly constrained. They're also difficult and time-consuming to produce because we need to adopt a trial and error approach to match the observed data, which requires a lot of tweaking. It's also very difficult to generate systematic multiple realizations that we need to, of the sort we need to do for uncertainty and risk analysis. And finally, because the models are merely reflecting the arbitrary geometric parameters that we applied to build them, they provide little information about parameters that are important for controlling the fluid flow, such as fracture connectivity and anisotropy, but which cannot be measured from the observed data. So we wanted to see whether we could adopt an alternative approach to generate fracture models by actually simulating the growth of the fracture network dynamically based on fundamental geomechanics, as we see here. And this approach should have several advantages. Firstly, because the model is based on fundamental geomechanical principles, it should honour the geology and the structural evolution of the reservoir. It should also be relatively easy to set up and run. Because it's a deterministic model, all we need to do is define the geometry of the layer, the mechanical properties and the deformation. Because we're simulating the growth of the network, we can easily generate multiple geologically realistic models that represent different stages of the fracture development for use in uncertainty and risk analysis. And finally, because it's a dynamic model, it actually predicts many of the parameters such as fracture size distribution and connectivity that are important controls on the fluid flow, but which cannot be calculated directly from the model, from the observed data. So in order to build these models, we need a conceptual model for layer-bound fracture network growth. And we start by assuming we have a single planar homogeneous layer that contains a population of small circular microfractures that are shown in red here. We then apply a horizontal strain to that layer, which generates a stress concentration around the edges of these microfractures that causes them to start to grow. And they will grow bigger until they span the entire layer. But then, because they are unable to propagate out of the layer, they will start propagating laterally, and they can be approximated by elongated rectangular fractures propagating laterally, as shown in blue here. Now, as the fracture network grows, these fractures will start to interact, and we can model two types of interaction. Firstly, stress shadow interaction between parallel fractures that propagate into each other's stress shadow. They will typically both stop propagating at this point and connect up via a relay zone to form one longer fracture. Propagating fractures may also intersect with perpendicular or oblique fractures, in which case they will terminate against a second fracture, forming a junction, as we see here. So in order to model the growth of the fractures, we combine linear elastic fracture mechanics theory with subcritical fracture propagation theory. Now, these are both well-established theories that have been confirmed by many observations and laboratory studies. Linear elastic fracture mechanics theory gives an analytical expression for the stress concentration around the fracture as a function of the fracture geometry, the in situ stress, the elastic properties, and crucially, the fracture size, in this case, the radius of a circular fracture. Subcritical propagation theory gives an analytical expression for the fracture propagation rate as a function of the stress concentration raised to a power known as the subcritical index. Now, for most rock types, the subcritical index is typically greater than 10, so the fracture propagation rate is highly nonlinear. Combining these two expressions, we can get a differential equation for the fracture size through time, which can be solved to give an expression for the rate of fracture growth through time. And this applies both to mode 1 dilatant fractures and to mode 2 shear fractures. Now, the advantage of the analytical solution is that because it's analytical, it's much faster to calculate than a numerical solution, and we can therefore build models that contain many thousands of discrete fractures and run them in a realistic compute time. But even more importantly, instead of applying the formula to individual fractures, we can apply it to fracture population functions describing the fracture network as a whole. And that allows us to model the evolution of fracture networks of unlimited size. So what are these fracture population functions? Well, a common type is the cumulative density distribution function, which gives us the density or the number of fractures of a given size or greater. So in this example here, we see that the density of fractures of a radius 0.1 meters or greater is approximately 3 fractures per cubic meter. Now, this can be expressed in terms of the number of fractures per cubic meter, which is often known as the P30 density, or the total area of fractures per unit volume, which is known as the P32. And these two functions are both related, so if we know one of the functions, we can calculate the other. Now, studies of real initial fracture networks have shown that they typically follow a power law distribution, as shown in these two examples, which are taken from an actual subsurface fractured layer. Now, we can combine the power law distribution for the initial fracture population with our expression for the growth of the fracture through time to get an expression that describes the evolution of the cumulative fracture density distribution function through time. And there are several things to note here. The first is that this expression is not itself a power law function. So, in other words, the initial power law distribution of the fractures is not stable through time. If the subcritical fracture propagation index is less than 2, the smaller fractures will actually propagate faster relative to the larger fractures, and the size distribution becomes more uniform through time. However, if the subcritical index is greater than 2, which will be the case for most geological examples, the larger fractures propagate faster relative to the smaller fractures, and the size distribution becomes more divergent through time. And in practice, this can be seen as an example of fractures nucleating intermittently. As fractures reach a critical threshold at which they start to propagate much more rapidly, we get the intermittent formation of individual fractures within the fracture layer. Now, in the case of layer-bound fractures, the equations are simpler. Because the stress concentration is proportional to the minimum dimension of the fractures, which in the case of layer-bound fractures is the fracture height, which is controlled by the layer thickness, this is uniform and constant, and therefore the propagation rate is the same for all layer-bound fractures. This allows us to derive analytical solutions for the fracture area and the fracture volume or fracture porosity, as well as for the fracture density. And we can use these expressions to model the growth of the layer-bound fracture network through time. What we find is that as the fracture network grows through time, the fractures start to accommodate more of the applied horizontal strain. And they do this by developing stress shadows. Now, the stress shadows, which are shown in blue here, are the zones around the fractures in which the applied horizontal strain is accommodated by displacement on the fractures rather than being accommodated elastically in the rock. And as a result, there is no stress in the rocks that allows further fractures to nucleate or propagate. Now, the width of these stress shadow zones can be calculated using linear elastic fracture mechanics, and it is proportional to the fracture height, but crucially independent of the in situ stress, and is therefore constant. Now, obviously, the total volume of the fracture of the stress shadows will increase through time as the fracture network grows, until eventually we reach a point where there is no more space for fractures to nucleate or propagate between the existing fracture stress shadows, at which point the fracture network cannot grow any further. It has reached a saturated stage. All further applied strain is then accommodated by displacement on the existing fractures. Now, note that when we reach the saturated stage, not all the volume is filled by stress shadows. There are still gaps between the stress shadows, but these are too narrow to fit additional fractures plus their stress shadows in between the existing stress shadows. So we can define an exclusion zone around each fracture in which no new fractures can nucleate. And this exclusion zone has a width twice that of the stress shadows. The fracture network will become saturated when the entire volume of the layer is filled with fracture exclusion zones. However, calculating this point is difficult because the fracture exclusion zones, unlike the stress shadows, can overlap. So the fracture stress shadow volume can be calculated very easily. We just multiply the total fracture area by the stress shadow width. But because the exclusion zones around individual fractures can overlap, the calculation of the exclusion zone volume is much more difficult. We can calculate it, however, by looking at the fracture spacing distribution. Now, this is another cumulative density distribution that determines the spacing between individual fractures. And we can develop an expression for this, a differential expression for the evolution of this function that cannot be solved analytically, but it can be solved numerically to give us a simple numerical expression for the growth of the exclusion zone volume through time. And we can see, use this to look at how the spacing distribution of fractures evolves through time. So in the early stages of fracture growth, when we have relatively few fractures and the stress shadows are well spaced, we have an exponential spacing distribution of the fractures. But as we add more fractures and the fracture spacing, the fracture density becomes higher, the spacing distribution evolves towards a more linear function until we reach the saturation point where we have no further space, further spaces large enough to fit additional fractures, stress shadows. Now, with this expression, we can then calculate the rate of fracture deactivation due to both stress shadow interaction and fracture intersection. Now, I'm not going to explain the details of this, but it is described in detail in our book that we've published about fracture network evolution. However, needless to say, the fracture deactivation rates are proportional to the existing fracture populations. As the as the fracture density increases, the fracture deactivation rates will also increase. And we therefore need to recalculate the fracture deactivation rates regularly as the fracture network grows. To do this, we discretize the model into time steps. And so using this technique, we can calculate the evolution of the cumulative density distribution functions describing the fracture network implicitly without needing to calculate or model the individual fractures. To calibrate the results of this, we can compare the implicit fractures, implicit cumulative fracture populations calculated in this way with the fracture population functions calculated empirically for explicit fracture networks. So in this example, on the left here, we see an explicit DFN generated using the geomechanical model that we've described here for including initial circular microfractures that have grown and have been controlled by stress shadows around the larger layer-bound fractures shown in blue here. And we can use statistical analysis to extract the cumulative density distribution functions for this fracture population, which is shown by the crosses on this plot here. So the red crosses represent the fracture area and the blue crosses represent the fracture density, the P30. The continuous lines here represent the equivalent functions calculated implicitly without modelling the explicit fracture network. And you can see we get a very good agreement between the two functions. There is a bit of scatter in the explicit fracture network, which we would expect because we are modelling individual fractures. We can do the same for layer-bound fractures. We see here on the left an explicit DFN with a single set of parallel layer-bound fractures which grow until they interact by stress shadow interaction with other parallel fractures. We again get a very good agreement with the cumulative density distribution functions calculated empirically for the explicit fracture network on the left, shown by the crosses, and the continuous functions calculated implicitly using the techniques that I've described, shown by the lines here. We can do the same for a fracture network containing two perpendicular fracture sets that interact by intersection as well as stress shadow interaction, and again we get a very good agreement between the explicit fracture network and the implicit fracture model. We can even calculate an anisotropic fracture network where we have a primary set of layer-bound fractures that evolved first, and then a secondary set of much shorter layer-bound fractures that connect these earlier, longer primary fractures. Again, the implicit model gives us a very good agreement with the explicit data. So, to summarise, by combining linear elastic fracture mechanics with subcritical fracture propagation theory and calculating the rates of fracture interaction, we can model the evolution of the population of layer-bound fractures dynamically without needing to model individual fractures. And this allows us to model the evolution of very large fracture networks across large geological structures. These results have been verified both by comparison with equivalent cumulative density distribution functions calculated empirically for DFN models, but also by comparing them with fracture populations observed in outcrop and subsurface examples, where they've been shown to give a very good match with the observed fracture populations. And this allows us to model fluid flow and geomechanics of naturally fractured layers in the subsurface much more accurately. So I'd just like to finish by thanking the sponsors of this project, and just by saying that the code that we've used to run these models is available as open source code to download from GitHub. So thank you for your attention.